is Victoria Laye, and I'm here to talk about a potential model for life on Mars and how we're using a combination of genomic and mutagenic analysis to look more closely at that model. So first of all, what do aliens look like? Pop culture depicts aliens and extraterrestrial life like this, but we suspect it will look more like this. So this is Halobacterium NRC1, isolated from the San Francisco Bay Salterns, and then this is Halorubrum lacus profundi, and it was isolated from Deep Lake, Antarctica. So these are Haloarchaea, or salt-loving members of Archaea, the third domain of life. And Haloarchaea make good models for extraterrestrial life because they're thought to be a very ancient form of life and are found in extreme environments. So NRC1 and H. lacus profundi, or HLA, have been subjected to stratospheric conditions such as pressure change, freeze-thaw, and radiation, both in the laboratory setting and with weather balloons, and have been shown to survive relatively well. And this was recently published in the International Journal of Astrobiology. They're also able to survive within brine inclusions in salt crystals, as you can see here in the colored portions. Those are living Haloarchaea. So these stressors are similar to the kind of stresses that would be experienced on Mars. Specifically, the extreme environment in which HLA is found is analogous to the conditions on Mars where there's thought to be periods of flowing liquid water, shown in the recurring slope lineae at Newton crater. So this liquid would most likely be brine, considering that the flows can be observed even at sub-zero temperatures. So there's a number of sodium chloride, magnesium perchlorates, and other salts that have been reported to be present on Mars that could allow the water to remain liquid at such low temperatures. So HLA is not only able to survive extremely high salt concentrations, but also low temperatures. It's even been recorded to grow as low as -1 degree Celsius. So because HLA is a cold-adapted Haloarchaea, it's very promising as a potential model for life on Mars. And by studying its evolutionary genetic adaptations, we're looking for specific ways in which it has diverged from its temperate or mesophilic counterparts, therefore giving an indication of what kind of evolutionary change results in the ability to survive these extremes. So HLA has a fully sequenced genome that's been compared to more mesophilic Haloarchaea in order to find residues that are conserved within the mesophiles but then diverged in HLA, suggesting that there's some evolutionary advantage to the residues in the cold-adapted organism. So we can look more deeply at a single enzyme by comparing the protein sequences from HLA to homologs in other mesophilic halophiles. Specifically in this study, we're looking at β-Galactosidase, which is that one. We found 6 residues that were diverged in the cold-adapted β-Galactosidase. So you can see there's one in the beta sheets of the Tim barrel here. There's a couple in the alpha helices of domain A, and then 2 in domain B. So they're found all throughout. There's no real pattern there. But β-Galactosidase is a catalyst that facilitates hydrolysis by breaking a glycosidic bond in sugars such as lactose. And that catalytic activity at low temperatures is generally even less effective than other enzymatic activities just in general because of the thermodynamic effect. So we performed mutagenesis on β-Galactosidase, expressed each mutation in a haloarchaeal expression system, and purified it to test the effect of changing those single divergent residues to the ones found in the mesophile through comparison to the wild type. And we used classical biochemical analysis through steady-state kinetics to quantify those effects. So for those of you who may not be familiar, steady-state kinetics uses this formula under conditions of substrate excess. So E is the enzyme, S is the substrate, and then P is the product. And ES is what the steady state is referring to. So at K minus 1 and K1, you're measuring the rate of dissociation of the substrate from the enzyme, and at K2, you're measuring the rate of reaction. So we can think of this as like a lock and key situation, where you want the key or the substrate to fit well with the lock, the enzyme, but still be able to remove the key or the product after the lock is unlocked and the reaction is completed. Since I'm looking at steady-state kinetics with high substrate concentrations, I can calculate the Km and Kcat. That's here. So the Km is similar to the dissociation constant of the substrate from the enzyme, and a lower Km is better as it indicates less dissociation. So Kcat represents the rate of the reaction under steady state conditions. And then Kcat over Km is the ratio of the two and represents the efficiency of the enzyme to perform the reaction. So the higher the Kcat over Km, the more efficient the enzyme is as a catalyst. And then we can look at these three constants compared to the wild type, comparing the wild type to the mutated enzyme at temperatures from 0 to 25 degrees Celsius in 2 molar KCl solution. So this graph is showing the Kms of the mutated enzymes in red compared to the wild type in blue. So a brief overview of our results showed that all of the mutated enzymes affected temperature activity compared to the wild type, with all of them exhibiting an increased Km at 0 degrees Celsius, the degree of difference varying, as you can see. And then the wild type exhibited a direct relationship between the Km and the temperature, which would be characteristic of a cold-adapted enzyme, where it has the lowest Km at the lowest temperature, and then a higher Km at higher temperatures. 4 of the 6 mutated enzymes showed inverse character compared to the wild type with a higher Km at low temperatures. So that was exactly what we were hoping to see in changing it from the divergent cold-adapted residue to the one found in the mesophile. And these results confirm the evolutionary importance of at least 4 of the 6 divergent amino acids in the improved function of the β-Galactosidase enzyme at colder temperatures. So now I'm going to go into more detail about one of my mutants. So one mutation in particular was at residue 482, which is located in a beta sheet in domain B. And in all these graphs, the mutated enzyme will be shown in red and the wild type in blue. So this mutation showed the highest increase in the Km at lower temperatures, suggesting that the mutated enzyme was less effective than the wild type at lower temperatures, which is in line with the hypothesis that changing that single residue will negatively impact the cold adaptedness of the enzyme. The change in the Kcat, however, is much more subtle than the Km, though you are still seeing a change at the higher temperatures, where the mutated enzyme has a better rate of reaction at those higher temperatures compared to the wild type, which again fits with our hypothesis as we're changing it from the residue found in the cold adapted enzyme to the one found in the mesophile, and an increased rate of reaction when you're losing that cold adaptedness at higher temperatures makes sense. And then finally, the enzyme efficiency was decreased for the mutated enzyme when compared to the wild type over the lower temperatures, you can see, and increased at the higher temperatures. And this trend was mainly influenced by the Km. As you could see before, it was a much more drastic difference between the two, but the Kcat is still taken into account and most likely shows its effects at those higher temperatures. So these 3 constants, when compared to the wild type, paint a picture of a less cold-adapted enzyme, supporting our idea that these diverged residues are diverged to increase the ability of the β-Galactosidase in HLA to function in the cold. The next step is to examine the enzyme model structurally. Are there patterns that can show us why certain residues in certain positions can affect the temperature range of the enzyme? So if you think of proteins or enzymes like molecular machines, which need to flex and move to be catalytically active, they need space to work effectively, and at high temperatures, the surrounding chemical groups and atoms are moving enough that there's plenty of space to work with. But at lower temperatures, as we talked about in the opening talk, at lower temperatures, the surrounding molecules are more densely packed and frozen, like water in a liquid compared to in an ice state where the molecules are more structured. So it stands to reason that the enzyme would need to be more flexible to function at those lower temperatures to counteract those effects. So when we look at the homology model, comparing valine at position 482 here to leucine at that same position in these images, what you're seeing is the residue in question and then residues and side chains within 6 angstroms of that, and the white area represents the edges of the van der Waals shells for each side chain and each atom. So you can see with valine, you're getting this space here that's unoccupied. And you're getting a similar space in leucine here, maybe a little bit smaller. You are losing that space here. So there's more potential flexibility here and fewer potential interactions with these residues up here, whereas with the leucine, there's more potential for interaction here, a greater chance of reduced flexibility. And the leucine is the one that's in the mesophile, and the valine is the original one in the cold-adapted enzyme. And then if we look at it from another angle, you can see even more clearly that this valine here, there's this additional space that isn't present when you have that additional carbon when it's a leucine. So you're losing that space, and then you have more potential for interactions, more potential, less potential flexibility. So the studies performed on these 6 different mutations are providing deeper insights into how enzymes may function at lower limit of temperature in an extremophile living in Antarctica. So in conclusion, when thinking about the potential for life on other planets, we can first look at life in the extremes on Earth to give us a better framework for how this kind of life may survive. In our approach, we can first look at those divergent regions in the proteins encoded in the genomes of microorganisms adapted to extreme environments, and then use experimental methods to confirm their importance in the ability to survive these extremes. And in doing so, we're able to use past evolution as a guide, pointing us towards novel adaptive mechanisms, leading to new discoveries, and expanding our understood ranges of survivability, thus giving us a better basis for how life may arise, even outside what we consider life's limits. So I'd like to thank my lab group for supporting me with this, and the University of Maryland and NASA for providing funding. Any questions?
Thanks for the nice talk. I have a question about your KM measurements. I'm wondering, what is your reporter assay for studying the KM? That's my first question. And also, are you limiting yourself to just a single residue mutagenesis at 482 based on your bioinformatic analysis? Sorry, I may not have. You may have covered it already, but didn't catch it.
So the answer to the first question, I'm using a colorimetric assay using ONPG at absorbance 420. So I'm doing like measuring the change in color there, and then using the V0 to calculate the KM using Lineweaver-Burke graphing. And the second question, I have all of those mutations that I talked about, the 6 different ones, they're at 6 different residues. I just talked about 482 for the sake of time, just going into one in specific. I do have a poster that I'll put up later if you want to see the other 6 or the other 5. So there you go. Questions?
Hi, I have 2 questions actually. So what are the uncertainties in measuring the KCAT and KM values? Are there any? I'm not really familiar
the problem
with
with like putting standard error bars and things like that on these graphs is that these values are based off of, so the way that they're calculated is you do those colorimetric assays with different substrate concentrations, and then based off of the V0s that you calculate from that, you create a Lineweaver-Burke graph, and then based off of the X and Y intercepts of that Lineweaver-Burke graph, that's where you get the KM and KCAT. So it's, it's a little bit difficult to get the uncertainties there.
Okay, so as an astronomer, I'll ask you later about what half of those words mean.
Sorry.
Were there any mutations in the Tim barrel region? And if
There was one. So the whole blue region, let me go back. So the Tim barrel is these beta sheets and then the surrounding alpha helices with them. And the reason why a mutation in the Tim barrel would be of interest would be because that's where you would get closest to the active site. And there was one here, A263S, that was in the beta sheets of the Tim barrel. That one didn't have a very strong temperature-dependent effect. It just had a, in general, deleterious effect. So that's why I didn't go into that one in detail here, but it was interesting.
Okay, thank you.
Hi, can you go to the slide with the 2 comparative structures real quick?
Which one? Oh, yeah, I know which one.
Yeah, one of these. So yeah, you guys did a valine to leucine mutation. What if you did like a valine to something smaller, like an alanine or something? Do you think that it would show kind of an opposite
That's what
difference?
we're hoping would happen. That would be a possible next step, because all of these mutations that we did were based on that bioinformatic analysis, going from the cold adapted to a mesophilic. But now that we're seeing that that does have the effect that we were expecting, the possibility of creating a more cold adapted enzyme exists potentially. So that would be a possible next step, would be to then reverse that, go in the opposite direction of the patterns that we're seeing, take it smaller, and see if that increase in space causes an increase in flexibility that could then result in an enzyme that works better at those colder temperatures.
Cool, thank you.
Thank you for that talk. Continuing on that last question, I was wondering, is there any advantages to having a less flexible enzyme at higher temperatures? It seems like it would always be better to have less kind of steric hindrances going on.
No, I mean, like was talked about in the initial talk, having that increased structural aspect at a higher temperature, you do get that. There's the potential for more stability and less denaturation at those higher temperatures. So it would potentially work in reverse.
I have a question for you. Why did you guys pick this enzyme, and are there other enzymes that you're thinking about doing similar
We picked this enzyme because our haloarchaeal expression system doesn't have a beta-galactosidase, and there's that very easy colorimetric assay as a sort of proof of principle. But we could do it with other ones. It's definitely possible.
Okay, we have time for more questions if there are any.
Have you used any control enzyme to for your experiment related to enzyme activity? Means you compare your results with mesophilic enzymes and psychrophilic enzymes?
Well, the problem is there aren't a lot of enzymes that have been looked at enough to be a control, at least in these specific conditions. Because like I said, I had to use a 2 molar potassium chloride solution in order to do these reactions, and generally you wouldn't use that high of a salt for enzymatic activity assays. And I wouldn't want to necessarily compare it to something that doesn't have that high of salt, because you don't know what kind of confounding variables you're adding in at that point.
And which method you use for to study there is a change in protein conformation as well as amino acid sequence?
So this is homology modeling using Swiss PDB Viewer. So that's a free software that's available online. And so we made a homology model of our enzyme using Thermus thermophilus because it has a characterized and crystallized structure of its beta-galactosidase. So we use that to create a homology model. And so this is all very theoretical. We haven't been able to get our enzyme crystallized. So this is all super theoretical. This is just the most likely one given the sequence that we've put into the system. And obviously that would be a really good next step, is to get it crystallized. So if anyone knows any good crystallographers that they want to refer to me, I'd be happy to take their number.
What about cryo-EM? Have you done cryo-EM on this?
I've tried to, but nobody will respond to my emails. I really want to get this crystallized, you guys. Trust me.
Hi, just a super quick question. So I'm a geologist, I work in XRD. What are the obstacles to crystallizing your amino acids?
I think it's the salt. I've talked to a lot of crystallographers, and whenever I bring up the fact that there's a lot of salt in it, they get kind of excited. They think that it's good. But then in practice, there seems to be some sort of hindrance. I don't know a ton about crystallography, so I don't know what's holding it back. Maybe it's the size, I'm not sure. But I mean, we've crystallized things that are smaller and bigger than this. So the only thing that I could think of would be the salt.
Okay, thank you.